All right, welcome. Last week we discussed functions where the variable or the variable equation or expression we were considering was the base of the exponential expression. So x squared, for example, or 1 over x squared plus 1, something like this. And the exponent then was a constant. But this week we're going to be talking about exponential functions where the variable is the exponent and the base is a constant. So we are going to define an exponential function of the form f of x is equal to a to the x, where a can be greater than 0. It cannot be 1, however. Okay, so it's not a negative value. And it can be somewhere between 0 and 1, but not equal to 1. And this is how we define this type of function. Okay. These functions for life sciences and health sciences are really important because they are used to describe growth and decay. We're going to be doing more of these problems when we introduce derivatives, but they will be very helpful to define, for example, how quickly a population doubles in size, types of problems like this. Now, when we said that a is not equal to 1, we said this because anything where we have a base of 1 and the exponent x, it's just equal to 1. But we can have a to the x multiplied by a negative value. Okay, so we can have something where we have a to the negative x, and then whatever that is, we can multiply this by negative 1. Please note that that is not the same as having negative a and then taking that to the power of x. Okay, these two things are not the same. This one is fine. This one is not allowed. Okay, let's look at an example to have a better understanding of this. We're going to plot 2 to the power of x, 3 to the power x, and then 2 to the power of negative x. And remember, by our exponent rules, this is the same as 1 over 2 to the power of x. All right, now let's consider what this function will look like if we have negative values or if we have positive values. So let's say we have x that is really, really negative. Whatever a is, we're going to get a to the negative infinity, and then we'll look at the different examples of a in a moment. Let's also take a look if we have negative 1. Okay, so this will be different for this one compared to this one. For example, we'll actually be on opposite sides of the x-axis. Let's look at what happens if our x is equal to 0. In all cases there, we'll have a to the 0, something to the 0 is 1. If we have positive 1, we'll have a to the positive 1. And if we have 2, we'll have a squared. So for our two cases where a is positive, we're both going to start and x is equal to 0, and they're both going to be equal to 1. Okay, so we're going to be here. If x is equal to 1, we have a to the 1. So in the case of 2, we would be at 2. And then if we have 2 squared, we would get 4. Okay, so things would keep getting bigger and bigger. On the other side, if we had a to the negative 1, that means 1/2, so we would be here. If we had negative 2, we would be even smaller. So as x gets more and more negative, these values get smaller and smaller, and our function looks something like this. In the case of 3, the values are the same at x is equal to 0, but then at x is equal to 1, we go to 3. If x is equal to 2, we go to 9. So this grows much faster. And then on the negative side, if x is equal to negative 1, we're at negative 1/3. And so it's smaller than our blue line here. So we'll get something that looks like this. Okay, so the red one is our g of x is equal to 3 to the x. Our blue one is our f of x is equal to the x. Now for the case of our 1 over 2 to the x. Okay, we are also going to be at the same spot if our x is equal to 0. If our x is equal to positive 1, then we're going to get 1/2. If our x is 2, we're going to get 1 over 4. So on our positive x-axis, we get smaller and smaller. But then on the opposite side here, if x is equal to -1, then we're going to end up getting 2. If x is equal to -2, we'll end up getting 4. So it's the opposite, basically, of the blue line. We get something that looks like, you know, this. This is our h of x. All right, now notice that these expressions here, they grow much faster than polynomials. So things like x squared, x cubed, even x to the 4. Okay, so notice these functions grow much faster than the ones we were looking at last week. We were looking at okay. Now let's take a look at how we solve exponential equations. So if we have an a that's greater than 0, it's not equal to 1, and we have an expression, say a to the x, and it's equal to a to the y. Our bases here are the same. So what does that mean? It means that the exponents would be equal, and we can solve for the variables in the exponents. So in the first example, part A, because our bases are the same, this is just going to give us 3x is equal to 7. So x would be 7 over 3. In this next case, even though the bases look different, they can still be expressed in terms of 3's. So note, for example, that if we took 3 squared, we would get a 9. And then if we took 3 to the power of 3, we would get 27. So we can change these expressions to, instead of reading 9 to the power of x is equal to 27, our 9 can be changed to 3 squared, and then we take that to the power of x. The 27 can be changed to 3 to the power of 3. And now, our left side, we're going to get 3 to the power of 2x, and then we're going to get 3 to the 3. Our bases are the same, so this just means our exponents, 2x is equal to 3, and then I can isolate for my x to get 3 over 2. Similar for this question, even though these bases don't look the same, they can both be expressed in factors of 2. So if you look at 2 to the 5, for example, that's 32. And if you look at 2 to the 7, that's 128. Now, how did I know that? Guess and check. I know that, 2 to the 2 is 4, and then times 2 is going to be 8, and then times 2 again is 16, and then times 2 again is 32. So if you notice that one of these could be written as a factor of 2, then the other one, if you're able to do this method, should be able to be written as a factor of 2 as well. So you need a little bit of playing around in order to get that. But now what we can do is, instead of writing 32 to the power of 2x minus 1 is equal to 128 to the power of x plus 3, I can replace these values with 2 to the 5, 2x minus 1 in the exponent. And then for 128, I can replace that with 2 to the power of 7, and then x to the power of 3. What does this mean? This means that I have 2 to the power of 5 times 2x minus 1, and then 2 to the power of 7 times x plus 3. Now that my bases are the same, we don't have to write them. We can just write out the exponents like this. And now we can expand them and isolate for our x. So I'm going to have 10x minus 5, 7x plus 21. Let's bring all of the x's on one side. So I'm going to get 10x minus 7x. That's going to give me 3x. and then I'm going to have 21 plus 5. So that will give me 26. I'm going to divide by 3. And then I get the answer that I want. Okay. Now we're going to talk about a very special number in mathematics. It's called the number e. Sometimes it's also called Euler's number. And it's roughly equal to the value of 2.71. And having e to the power of a variable, so e to the x, for example, this is very useful in life sciences for reasons that we will shortly see, especially when we're talking about growth and decay of populations. We're also going to talk about its definition a little bit more when we get to derivatives, but the definition, for now, we'll just look at it like this. If we have 1 plus 1 over m, all of this to the power of m, and if we keep looking at m as it gets bigger and bigger and bigger, it turns out that it approximates this value. And this is the value that we've just referred to it as e. It's like the same with pi. Pi is infinitely many decimal places. We don't write them all out, so we just refer to that value as this thing called pi. Now, the functions e to the x, e to the negative x, negative e to the negative x, and negative e to the x, we're going to draw what they look like with respect to each other. So for e to the x, let me zoom in a little. For e to the x, always check what happens when x is equal to 0. So when x is equal to 0, we have e to the 0, and that's just equal to 1 here. If x is negative, so if it's e to the negative 100, that's a small number because that's equivalent to 1 over e to the 100. So as x gets more and more negative, we get smaller and smaller, closer to 0. But if we look at, e squared, that's like 2.7 squared. And then e to the power 4, that's even larger. So it grows very quickly. It looks something like this. Okay, so this is what e to the x looks like. If we look at e to the negative x, this time, if x is negative, if it's along here, the value is going to be very large. If I look at e to the negative 0, I'm still going to be at 1 here. But then if I look at the positive values, I get e to the negative big value. So it's flipped about our y-axis. It looks something like this. And then it blows up. Now, if I have negative e to the x, that just means I'm flipped about the x-axis. So it's going to look the same as this one here, but we're going to be below the x-axis. So if x is equal to 0, we're going to get negative e to the 0, which is 1. So we're going to cross right here at negative 1. Okay, and this is positive here. And then we're just going to look something like this. So this is e to the negative x. And similarly, if I look at e to the negative x and then I add another negative in front of it, it's the same thing. This is going to be reflected about this axis. So it'll look something like this right here. Okay, so this is negative e to the negative x. If you have these values, or these functions, excuse me, shifted by constants, so say we have e to the x plus 1. All that means is that I'm going to take this plot right here, and I'm just going to shift it up by 1. Okay, so let's change this color. We'll say it's red. This is our value of e to the x plus 1. Similarly, if I were to go e to the x minus 1, I would start from here, but I would shift down 1, and this is going to be our value, or what our graph looks like, of e to the x minus 1. Okay, so those are common graphs of e to the x and what shifts look like. Alrighty, last but not least, let's do a bit of a word problem. Okay? Not freak us out, but just see where these types of functions can be useful. So oxygen consumption. So biologists studying salmon have found that the oxygen consumption of the salmon increases exponentially with the speed that they swim, according to a function that can be written like this. So f of x is equal to 100e to the power of 0.6 times x. Now what is x? X is the speed in feet per second, and we want to find the following. So we first want to find the oxygen consumption when the fish are still. So when they're not moving. So if a fish isn't moving, they don't have speed. They have speed of 0. So in the case where when the fish are still, their speed is 0. And speed for us is represented by x here. So what they want us to find is what our function will equal if the speed is 0, where the function represents oxygen consumption. So all I have to do here is plug in 0 for my x value. So I have 100 e to the power of 0. Anything to the power of 0 is 1, so I have 100 units. They don't tell us the units, so we'll just write 100 units like this. And now what we want to do is we want to find the same thing, except if now they have a non-zero speed, specifically 2 feet per second. So in our case, because this is the units that were given to us in the problem, we don't have to worry about converting anything. Okay, so I want to look at what happens if my x is equal to 2. So if I plug in 2 for my x, I'm going to get 100 e to the power of 0.6 times 2. So this is going to be 100 e to the 1.2. You can leave your answer like this, but just generally so you know roughly what this means, if you plug this into a calculator or on Google, you're going to get approximately 332 units. Now, what does this mean exactly? So this means that at the speed of 2 feet per second, oxygen consumption is about 332 units. Okay, I hope you found this helpful. Take care.